if you take smooth vector fields, any two vector fields, smooth vector fields, you look at you define a function see, these are vector fields, so tangent vector fields, okay? Usually for us vector field means tangent vector fields. So at each point P, xp is a tangent vector, yp is a tangent vector, so that gives the inner product there. How do you write? You write x sub p or x like this, whatever, okay? So what is this? This is nothing but the inner product on the tangent space, okay? So this gxy is now, what does it do? It's a function now, taking values where scalar functions, scalar valued functions. So gxy is a smooth function. For all choices of x and y. Then you say that this is a smooth choice, right? The smoothness refers to the smoothness of these functions. So this is a smooth choice of metrics on tangent spaces. So this is what is called a Riemannian metric on S. On the Euclidean space, we have the constant metric, right? It does not depend on a point. Every tangent inner product on every tangent space is the inner product coming from the ambient Euclidean space. Constant metric, right? So that is a Euclidean metric. You look at the upper half plane. So this is xy in R2. Y greater than 0, or in terms of complex numbers, z and c, imaginary part of z, positive. So define a metric as 1 over y square. That means, so what is the tangent space at any point z? So z, imaginary z greater than 0. We call it H. So this is an open subset of the plane, okay? So tangent space at any point is just the ambient vector space R2. Okay, so TPH is equal to R2 or C for all P, for all Z. Of course, you have the usual Euclidean metric, right? But we are now going to define different metrics at different points, a non-constant metric. So define G that means GZ, okay, point is Z now. As this is the same as that notationally, okay? I am denoting by this. So this is 1 over y square or imaginary Z square, the Euclidean inner product. P dot W is the usual inner product in R2. So multiply that by a function 1 over y square. Okay? This is the Riemannian metric on H. Poincare metric. This accent over the E, right? The what they call as the acute accent in French, accent. So that indicates that you pronounce it as A. You don't read it as Poincare, but Poincare. Okay, and don't read it as Poincare. Poincare. OI is, the sound is va sound. Poincare. So as I mentioned in the morning, this is an example or a model of the hyperbolic plane. You also have the disk model. Unit disk. So again, you take the, of course, here again the tangent space at any point is a whole plane. Okay, define the inner product. Take the usual Euclidean inner product and multiply by something, a function of Z. Okay. Is by definition multiplied by the function 1 over 1 minus mod z square the whole square. So this gives you what is called the hyperbolic metric on the unit disk. So this is not your Euclidean disk, but a hyperbolic disk. The two pictures are essentially equivalent. So you have an isometry from one to the other. If you this metric and compute the curvature, it's going to be -1, constant -1. So both the metrics will have the upper half plane with the Poincare metric or the unit disk with the hyperbolic metric will both yield you will yield the constant curvature -1. The curvature is constant -1. So both of these are locally isometric to the pseudosphere that we have looked at in the morning. So of course, we can do some calculations if we had time. Okay, you can calculate lengths in any of these metrics, right? Even straight line segments. For example, if you look at the upper half plane picture, okay, take a line segment on the y-axis, for example. This, suppose you fix some length, right? Length 1, if you like, or length half, or whatever, the Euclidean length, okay? But if you move the same thing this way or that way, the length will change, right? If you come closer to the real axis, the length of that segment will increase. If you go away from the real axis, the length will decrease. Okay, so actually, if you approach as you tend to the real axis, these lengths will tend to infinity. The Euclidean length is fixed, but the hyperbolic length will keep changing and going to infinity as you approach the real axis. So this, in some sense, this real axis is the line at infinity in this space, right? Is an infinite distance from any point. In the case of the disk model, as you approach the boundary circle, the distance goes to infinity. That means the line at infinity, in this case, is the unit circle, the bounding circle itself. L, the length goes to infinity. Length of any segment. You can also describe what the geodesics are. Geodesics, in this case, the upper half plane picture. Remember, we have your space is the open upper half plane. The real axis is not part of the space. So if you look at vertical lines, these are all geodesics. Okay? And also circular arcs with center on the real axis. Okay, the real axis is not part of your space, but if you look at, see, these open arcs you have to look at, right? The open upper semicircular arc for circles with center on the real axis. These are all again geodesics. So you have center here, center here, here. So these are all the geodesics in this case, the upper half plane, the Poincare upper half plane. Circles orthogonal to the bounding circle. So this includes diameters, lines through the center, right? So these are all geodesics. In addition, you have actual circles. These are degenerate circles. Okay? But in addition, you have circles orthogonal to a boundary circle. Circular arcs of circles which cut this orthogonally. So these are all again geodesics. So that's why in either case, whether you have the upper half plane picture or the unit disk picture, triangles will look like this. A triangle is going to be like this. Okay? A geodesic triangle, to be precise. A hyperbolic triangle. So sum of the angles is less than pi. The Gauss-Bonnet theorem, I think I had mentioned enough in the introductory lecture itself. We don't have anything more, any more machinery now to say anything more now. So the Gauss-Bonnet, I'm going to come back to this unit disk in a moment. But the Gauss-Bonnet theorem K compact connected to surface in R3. K is the curvature. K, not K. K is the curvature, right? S is a compact connected surface. The Euler so integral of the curvature function over the surface is sometimes referred to as the total curvature of the surface. So the average of the curvature at all points. Of course, factor of 1 by 2 pi comes in. So of course, you have to make sense of the integral there, what it means and so on. So we will not go into that. So this dA is what is called the surface area form, right? Just like you have the Euclidean case, dx dy, that gives the area measure. So on a surface also there is something called the area measure or area form. It's called, is actually what is called a differential 2 form, volume form it's called. In case of dimension 2, volume is area, so what is called the area form. A is surface area form if you want. So on the right hand side you have the Euler characteristic, which is by definition. So if you start with the surface and triangulate it, just like, so topologically, as I mentioned the other day, the sphere can be thought of as a tetrahedron formed by 4 triangles there. Okay, it's homeomorphic to that. A circle is homeomorphic to a triangle inscribed. So in general, we can look at surfaces formed by triangular faces, right? Various ways. You can take a polyhedron, like, and each face you can subdivide into triangles, right? Even if you take a what is it called, cube. So each face is a square. You can divide each square into triangles, so that the whole thing is made up of triangles, right? So of course a cube is homeomorphic to a sphere, right, or a tetrahedron. So of course you can do it in many ways, right? There is no single unique way to triangularize it. So topologically you can get it as a polyhedron if you like, but further divided into triangular faces. So what is called a triangulation in general. So there is a general theorem which says any compact surface can be triangulated. So once you triangulate, so what do you have? You have a number of triangular faces. You have the edges of those faces and the vertices of those faces. Okay? So in general, what is called a simplicial complex of 2 dimensions, dimension 2 in this case. So you can count the number of vertices, number of edges, number of faces. Right? Of course, this is not unique. You can divide any triangle into further smaller triangles and so on. But the quantity, so triangulate S. So you look at V minus E plus F. This is a constant, as the theorem of Euler says. So this is what is called so this is independent of the triangulation that you look at. Okay? Independent of triangulation. So this is a topological invariant. K is a geometric invariant. So the Gauss-Bonnet theorem says that the total curvature is equal to the Euler characteristic, geometric quantity on the left hand side, a topological invariant on the right hand side. So the importance of the theorem arises from the fact that it equates a geometric quantity with a topological number, invariant number. So of course it had led to a lot of developments in differential geometry. So but before I conclude, I would like to spend some time, say 10 minutes or whatever, 10 minutes, by looking at the disk model of the hyperbolic plane that we looked at, curvature -1, connections of that with complex analysis. Okay, let me just quickly try to say a few things without going into details. If I have, say, about an hour more, I can give you a nice picture. But let me at least try to give you the salient points of this. So the basic result which makes this application to function theory possible is what is called Alphonse Schwarz lemma. Little paper of Alphonse, which appeared in 1937 or something of that kind, in the Transactions of AMS, which made a connection between curvature and complex analysis. So before stating what this tells you, so if you look at the disk, we had a function there, 1 over 1 minus mod z square whole square, right? The Euclidean inner product multiplied by this factor there. So call it rho z or something. So your Riemannian metric on the unit disk is rho z, or let's denote by rho z this one. So rho z square times the Euclidean inner product. So a metric, hyperbolic metric, on D is given by the Euclidean time metric. Right? In general, you can take, if you have a domain in the complex plane, any open connected set in the complex plane, let's say, look at, let's say, any function sigma z, which is, say, positive, and you want, so you can try to define a metric using this function. So instead of, so sigma z square times the Euclidean metric. Okay? So just for convenience, we will refer to these functions themselves as a metric. Okay? So that function times the Euclidean metric is a metric. So each of these functions of this type will give you a Riemannian metric on the tangent space at each point of this domain omega. What Alphonse lemma says is the following. Okay, so if you have two domains, omega and 1 and omega 2, suppose you have a function which is analytic on omega 1, taking values in omega 2. Both are domains in the complex plane. So if you are given a sigma on omega 2, you can pull back that to omega 1. So we denote it by f star sigma. How is f star sigma defined? F star sigma of z is, by definition, sigma z sigma of fz, right? Sigma is on this side, times modulus f prime z. F is analytic, so you have f prime. So this again gives you a positive function on this, on the domain of the function f. So this is called the pullback metric. Okay, so each of these metrics gives rise to a curvature on that, right? Defines a curvature, gives some curvature, just like the hyperbolic metric gave -1, constant curvature -1. So they give some curvature. We don't worry about what it is. So you have the pullback metric. What Alford's lemma says is that if you have D, the disk on this side, you have some domain here, right? And some metric there. So here you have the hyperbolic metric rho. That's fixed, right? So look at the pullback f star sigma. If this gives you negative curvature less than or equal to minus c for some fixed c, then so negative curvature, so if this metric gives you a negative curvature, so its pullback is dominated by the hyperbolic metric. So in a sense, the hyperbolic metric dominates every other metric which gives you negative curvature. So this looks simple enough. The proof is also not difficult. It only uses the maximum modulus theorem, nothing more than that. But it has some astonishing consequences, applications to complex function theory. Suppose you have a omega and a metric on omega with constant negative, not constant, negative curvature, curvature bounded by less than or equal to some minus c at all points. A metric k is less than or equal to minus c. Curvature given by the metric sigma, writing as kc. So this is less than or equal to minus c for some constant c. And you have an analytic function defined on the whole plane. That means an entire function whose range is contained in omega, which has some metric giving rise to negative curvature. Then f is a constant. So in other words, a non-constant entire function cannot take values in such a domain, on a domain which has a metric yielding negative curvature. So a disk always has a metric of negative curvature. Okay? And therefore, by this result, any such function has to be a constant. Just take one line. Okay, but not just this. But there is, okay, so let me ask this question. What can you say about the values or the range of an entire function? It need not be the whole complex plane, right? For example, the exponential function doesn't take the value 0. Of course, it can be the whole complex plane. The identity function z takes everything, every value. It can't be the whole, I mean, it can be whole the complex plane, but it can omit one value. That's all. It cannot omit two values. If an entire function omits more than one value, it must be a constant. Okay, this is what is known as the Picard theorem, little Picard. An entire function on C omits a non-constant so this means the range is either entire complex plane or C minus a single point. So another way of stating this is that if f is an entire function and there are two numbers a and b, two complex numbers a and b, which are not in the range of f, then f must be a constant. So suppose you take a, b in C, a not equal to b, two distinct complex numbers. So to prove this, what do you have to do? You just have to, where is that theorem that I stated? If your range has a metric with negative curvature, then any entire function taking values in that must be a constant. That was the theorem, which is a consequence of the Alford's lemma. So in view of that, to prove this, what all you have to do is to produce a metric on C minus AB, which gives negative curvature. Okay? You can explicitly write down such a metric. I'll write down, but I don't know whether I remember it or not. I will have a look at it's a complicated expression. Z minus A mod Z minus A over 1 by 3 whole power 1 by 2 and a similar thing for B. Okay? 1 plus mod Z minus B for 1 by 3 of course the calculation you have to do is a little unpleasant, so to say, but nevertheless take it from me that I have calculated it at least once, maybe 15 years back, perhaps. So this metric on C minus AB, so this is your omega now, on omega gives k less than or equal to minus something, some negative constant there. So conclusion is that if any such function, any analytic function from C to omega has to be a constant. Okay? Of course, Lewis theorem is much, much weaker than this. So there is also a great Picard theorem. So I will just mention it and stop. Okay? So of course, the little and the great are adjectives to the theorem, not Picard. Picard's little theorem and Picard's great theorem. Picard is the same Picard. Picard, of course, you must have seen somewhere or the other. Differential equations. Although the Picard's, what is usually called Picard's theorem on existence and uniqueness solutions, is not actually due to Picard. Okay, so that's a different thing anyway. So, Émile Picard, a French mathematician. So, you have heard of the Parthasarathy-Weierstrass theorem, right? So, what does it say? You haven't seen Parthasarathy-Weierstrass theorem? Weierstrass theorem, okay. The behavior of a function in a neighborhood of an essential singularity. Right? You have seen this? So what the theorem, so how is it stated in alphas? I think it's stated something like that it takes values arbitrarily close to any given complex number or something. So in topological terms, what it says is any neighborhood of an essential singularity, the range of f is dense in the complex plane. So the great Picard theorem is a generalization of this, far-reaching generalization of this. It says that it's not only dense, it actually omits at most one value in any neighborhood of an essential singularity. Okay? Even the great Picard theorem can be deduced from the Alphonse lemma without too much difficulty, I should say. Picard theorem was more or less, I mean, the little Picard theorem was just a walk in the park, let's say. But a great Picard theorem, you need few more things, like the Montel's theorem, and so on. So you can prove Montel's theorem using the Alphonse lemma and so on. So a little more work is needed, but still it is much, much, much easier than the other proofs of the great Picard theorem. Okay? Essentially an easy consequence of the Alphonse-Schwarz lemma. But why is it called Alphonse-Schwarz lemma? You remember what Schwarz lemma says? If you have an analytic function from the unit disk to unit disk, it takes 0 to 0, then mod fz is less than or equal to mod z, and f prime 0 is less than or equal to 1. Equality holds only for rotations. Multiplication by fixed number of modulus 1. Okay, so this lemma is a simple corollary, simple special case of the Alpous lemma. So that incidentally also gives the geometric content of the Schwarz lemma. Right? Schwarz lemma is very simple, but it has very interesting consequences. Like, for example, you can use that to characterize all automorphisms of the unit disk. Analytic automorphisms of the unit disk. Analytic diffeomorphisms, if you like, because now you know the word diffeomorphism. All maps, analytic maps whose inverse is also analytic. They are called analytic diffeomorphisms. So you can, using Schwarz lemma, you can characterize all analytic automorphisms of the unit disk. They are the usual thing. You have the Mobius transformations, right? Z minus A over 1 minus A bar Z, right? This maps unit disk to unit disk. You can multiply by a complex number modulus 1. So a consequence of Schwarz lemma is that these are all the automorphisms of the unit disk. Okay, so there I stop. So all this, I don't know, I had studied some 25 years back, perhaps. Okay, so there I stop, and